November 8, 1942. Oran, Algeria. Operation Torch. Captain Thomas Hogan stood beside his M1 155-meter howitzer, watching hydraulic fluid drip steadily from the recoil mechanism onto the North African sand. The gun had fired 17 rounds during the beach assault. Exactly 17, before the seal failed and fluid began leaking. Now the massive artillery piece was effectively useless. Without hydraulic pressure in the recoil system, firing would destroy the gun, breaking the carriage and possibly killing the crew. Hogan's battery had 12 howitzers. By nightfall, 7 had suffered similar failures. Hydraulic seals, designed in peacetime for temperate climates and careful maintenance, were disintegrating in desert heat, sand, and combat stress. The same pattern was repeating across every American artillery unit in North Africa. Guns that worked perfectly at Aberdeen Proving Ground were failing catastrophically in combat. German artillery, even captured French guns pressed into Wehrmacht service, operated reliably despite similar conditions. The implication was humiliating. American engineering, supposedly the world's best, couldn't match European designs proven in World War I. But Hogan, a mechanical engineer from Detroit before the war, examined the broken seal closely and recognized something others hadn't. This wasn't design failure. It was material failure. The rubber compound couldn't withstand conditions. And that meant the solution wasn't redesigning the gun. It was redesigning one small component that nobody had considered critical. That broken seal would trigger engineering revolution that transformed American artillery into most reliable in the world. American artillery in 1942 represented culmination of 2 decades of development. After World War I, Army Ordnance Department systematically studied artillery technology, examining captured German guns, French 75mm designs, British howitzers. They concluded that future artillery must emphasize mobility, rapid firing rate, and accuracy. The M1 155mm howitzer, adopted in 1940, embodied these principles. It featured split-trail design allowing wide traverse, hydraulic recoil mechanism enabling rapid firing without relaying, and modern fire control systems permitting indirect fire at ranges exceeding 14,000 yards. The hydraulic recoil system was engineering marvel. When gun fired, barrel recoiled backward against hydraulic cylinder filled with oil. Fluid was forced through precisely calibrated orifices, converting kinetic energy into heat and controlling recoil distance. Counter-recoil springs then pushed barrel back into battery position, ready for next shot. System allowed firing rate of 4 rounds per minute, revolutionary compared to World War I artillery requiring manual repositioning after each shot. But the system depended absolutely on seals maintaining hydraulic pressure. Primary seal, ring of synthetic rubber compressed between cylinder and piston rod, had to withstand pressures exceeding 3,000 psi during firing, remain elastic across temperature range from 20° honors to 120°, resist degradation from petroleum-based hydraulic fluid, and tolerate contamination from dust and sand. Ordnance Department specified Buna N synthetic rubber, developed in Germany in 1930s and licensed to American manufacturers. Laboratory testing showed excellent performance. Seals lasted 10,000 cycles in controlled conditions. Combat conditions weren't controlled. North African temperatures reached 130° in direct sunlight. Sand infiltrated every mechanism despite protective covers. Maintenance schedules, calling for seal inspection every 500 rounds, were impossible to follow during sustained combat. Hydraulic fluid, subjected to extreme temperatures and contamination, degraded chemically, becoming acidic and attacking rubber seals. Within days of Operation Torch, American artillery units reported seal failure rates exceeding 30%. Some batteries lost majority of their guns to hydraulic failures rather than enemy action. German artillery didn't suffer comparable problems. Their guns, many designed in 1910s and 1920s, used older recoil systems with leather seals backed by metal springs. Leather was less efficient than synthetic rubber, but also less sensitive to temperature extremes and contamination. German guns fired slower than American equivalents, but they fired reliably. In artillery duel, reliability often mattered more than theoretical performance. American commanders faced crisis. Major General Lloyd Fredendall, commanding the II Corps in Tunisia, reported to Eisenhower in December 1942, "Artillery failures are compromising operations. We have numerical superiority in guns but cannot maintain them in action. German artillery, though outnumbered, achieves effective superiority through reliability. This must be corrected immediately, or we risk operational failure. Army Ordnance Department responded by dispatching technical team to North Africa in January 1943. Led by Colonel Leslie Simon, Chief of Ordnance Research and Development, team included materials engineers, hydraulic specialists, and field maintenance experts. Their mission: determine why seals were failing and develop solution deployable to combat units within months, not years. Simon's team began systematic investigation. They collected failed seals from artillery units across North Africa, cataloged failure modes, and analyzed material samples. Pattern emerged immediately. Seals weren't wearing out gradually from normal use. They were failing catastrophically from chemical degradation. Buna N rubber, when exposed to combination of extreme heat, contaminated hydraulic fluid, and ozone, generated by electrical systems and firing mechanism, underwent molecular breakdown. Polymer chains fractured. Material became brittle. Seals cracked and leaked. Laboratory analysis revealed the mechanism. Buna N is copolymer of butadiene and acrylonitrile, molecular chains alternating between these components. The acrylonitrile provides oil resistance, while butadiene provides flexibility, but butadiene segments are vulnerable to ozone attack. Ozone molecules break carbon-carbon double bonds, creating cracks that propagate through material. In temperate climates with clean air, this degradation occurs slowly, over years. In North African combat conditions with high ozone concentration from electrical equipment, extreme heat accelerating chemical reactions, and contaminated fluid attacking material simultaneously, degradation occurred in days. Simon's preliminary report, sent to Ordnance Department in February 1943, was blunt. Current seal material is fundamentally unsuitable for combat conditions. Buna N cannot withstand ozone exposure at elevated temperatures. We require different material with superior ozone resistance while maintaining necessary oil resistance, pressure tolerance, and temperature range. Alternative materials exist, notably natural rubber compounds and newer synthetic polymers, but procurement and testing will require minimum 6 months. In interim, recommend increased seal inventory and revised maintenance procedures. But 6 months wasn't acceptable. American artillery units were engaged in continuous combat. Tunisia campaign was escalating. Sicily invasion was planned for summer. Waiting 6 months meant accepting artillery unreliability through critical campaigns. General Dwight Eisenhower, Supreme Allied Commander, personally intervened. He sent message to Ordnance Department. Artillery reliability is strategic priority equal to ammunition supply. I require solution in weeks, not months. Authorize whatever resources necessary. That authorization transformed seal problem from technical issue to Manhattan project-scale emergency. Ordnance Department mobilized American rubber industry, university research laboratories, and National Bureau of Standards. They established testing facilities in Arizona desert simulating North African conditions. They contracted with every major rubber manufacturer to develop alternative compounds. And they assigned priority ratings ensuring seal research received materials, personnel, and manufacturing capacity ahead of almost every other wartime program except nuclear weapons development. The broken seal had become national strategic priority. The breakthrough came from unexpected source. Dr. Waldo Seaman, research chemist at B.F. Goodrich Company in Akron, Ohio, had spent previous decade developing polyvinyl chloride, PVC plastics. PVC was revolutionary material, moldable, durable, resistant to chemicals, but Seaman's research focused on rigid applications like pipes and panels. He hadn't considered flexible seals. When Ordnance Department distributed urgent request for ozone-resistant rubber alternatives, Seaman recognized that PVC could be plasticized, made flexible by adding chemical compounds that separated polymer chains, creating material with unique properties. Seaman formulated experimental compound, PVC polymer plasticized with modified phthalate esters, reinforced with carbon black for strength, and stabilized with organometallic compounds preventing thermal degradation. The material was flexible like rubber but chemically different, chlorinated hydrocarbon rather than unsaturated elastomer. Critically, it lacked carbon-carbon double bonds vulnerable to ozone attack. Seaman sent samples to Aberdeen Proving Ground in March 1943. Testing was brutal. Engineers machined seals from Seaman's compound, installed them in M1 howitzers, and subjected guns to accelerated wear testing. continuous firing in environmental chambers heated to 140 degrees Celsius, with introduced ozone at concentrations 10 times normal atmospheric levels, using deliberately contaminated hydraulic fluid. Standard Buna N seals failed after approximately 200 rounds under these conditions. Siemens PVC seals lasted 5,000 rounds without significant degradation. But there was a problem. PVC seals were stiffer than Buna N. They required higher force to compress, making installation difficult. They also had different friction characteristics, affecting recoil dynamics slightly. Guns with PVC seals recoiled approximately 2% farther than designed, potentially causing stress on carriage. Artillery officers objected. Changing seal material would require requalifying every artillery piece, recalculating firing tables, retraining maintenance crews. Colonel Simon faced resistance from his own organization. He overruled objections with engineering pragmatism. "Gentlemen," he told assembled officers at Aberdeen meeting in April 1943, "we have two options. We can maintain current specifications and accept 30% failure rate in combat, or we can adapt to material that requires minor modifications but reduces failure rate to essentially zero. The choice is obvious." He ordered immediate production of PVC seals for all artillery types, directed engineering teams to modify installation procedures and adjust recoil calculations, and authorized field modifications to guns already deployed. Production began in May 1943. Goodrich Company converted manufacturing lines from tire production to seal production, another example of wartime industrial flexibility. By June, first PVC seals were arriving in North Africa. Artillery maintenance units received priority shipments with instructions: replace all Buna N seals immediately, regardless of apparent condition. Within 6 weeks, majority of American artillery in Mediterranean theater had been converted. The Sicily invasion in July 1943 became first large-scale test of modified artillery. American forces landed with over 600 artillery pieces, from 105 mm howitzers to 150 mm long toms, all equipped with PVC seals. The campaign was intense. American artillery fired over 500,000 rounds in 38 days of fighting. Temperatures reached 110 degrees Celsius. Dust was omnipresent. Guns fired continuously during critical battles. At Gela, American artillery fired over 3,000 rounds in single day, repelling German counterattack. Seal failure rate, less than 2%. Contrast with North Africa 6 months earlier, 30% failure rate under similar conditions. The improvement was dramatic and immediately noticed by commanders. Major General Troy Middleton, commanding 45th Infantry Division, reported, "Artillery reliability has improved decisively. We can plan operations assuming full artillery support will be available rather than assuming 30% degradation. This changes tactical calculations fundamentally, but field experience revealed unexpected benefit beyond reliability. PVC seals, being stiffer, actually improved gun accuracy slightly. The additional recoil distance, initially considered problematic, proved advantageous. It reduced peak forces on carriage, decreasing wear on other components. Guns with PVC seals required less maintenance overall. Counter-recoil springs lasted longer. Elevating mechanisms showed reduced wear. Trail assemblies developed fewer stress cracks. Artillery crews noticed another advantage. PVC seals didn't require the elaborate protective measures necessary with Buna N. Older seals needed frequent inspection, cleaning, and protective coating to prevent ozone damage. PVC seals were essentially maintenance-free between overhauls. Crews could focus on ammunition handling, fire control, and tactical positioning rather than constant seal maintenance. German intelligence noticed the change. Captured documents from late 1943 include Wehrmacht reports analyzing American artillery. Enemy artillery demonstrates improved reliability and sustained firing rates. Previous pattern of declining fire effectiveness after extended operations has disappeared. Assess that Americans have resolved technical problems observed in Tunisia. Recommend increased allocation of counter-battery assets. The Germans were correct, but didn't understand specifics. They assumed Americans had deployed newer gun models with improved designs. In reality, only one component had changed, a seal costing approximately $8 to manufacture. That single component, improved through material science rather than mechanical redesign, had transformed artillery effectiveness. By September 1943, all American artillery worldwide, including units in Pacific Theater, received PVC SEAL conversion kits. Italian campaign, beginning that month, saw American artillery supporting operations with reliability unprecedented in military history. During Salerno landing, 105mm howitzers of 36th Infantry Division fired over 10,000 rounds per battery in first week, with 0 hydraulic failures. Such sustained fire rates were impossible with previous SEAL technology. German defenders, accustomed to artillery fire that diminished after initial bombardment, faced continuous, accurate fire that never slackened. The Normandy invasion in June 1944 represented ultimate test. American artillery massed for D-Day included over 2,000 guns, from 105mm pack howitzers jumping with paratroopers to massive 240mm howitzers bombarding coastal fortifications. All had PVC seals. All operated in conditions specifically challenging for hydraulic systems: salt spray from ocean, temperature fluctuations between cold English spring and combat heat, and firing rates exceeding any previous campaign. During first 48 hours of Normandy invasion, American artillery fired over 1.2 million rounds, more than entire North African campaign. Guns operated continuously, often firing until barrels glowed red and required replacement. Crews worked through exhaustion, loading and firing mechanically, but hydraulic systems held. SEAL failure rate during first week, 0.3%, essentially background noise from installation errors and battle damage. British artillery officers observed American reliability with professional envy. British guns used traditional recoil systems with leather seals and metal springs, reliable but requiring more maintenance and achieving slower firing rates. Lieutenant Colonel Basil Jackson, commanding British Artillery Regiment attached to American sector, wrote in after-action report, "American artillery technical superiority is decisive factor in sustained operations. Their guns fire faster and longer without maintenance than anything in British inventory. This is not superior metallurgy or design. It is superior materials science in critical components." German response was increasingly desperate. Artillery duels on Western Front heavily favored Americans. More guns, more ammunition, and critically more reliability. German artillery, suffering from resource shortages and manufacturing shortcuts imposed by strategic bombing, experienced declining reliability. Seals, hydraulic fluid, precision components, all degraded as German industry struggled under Allied air attacks. By contrast, American artillery improved. Each month brought minor refinements: better hydraulic fluids formulated specifically for PVC seals, improved installation procedures, optimized maintenance schedules. The Battle of the Bulge in December 1944 provided severe test. American artillery operated in extreme cold, temperatures below 0°C, which made rubber brittle and hydraulic fluid viscous. Previous seal materials would have failed catastrophically. PVC seals, engineered to maintain flexibility across wide temperature range, continued functioning. Artillery proved decisive in blunting German offensive. American guns, including those of Bastards of Bastogne defending critical road junction, fired over 350,000 rounds in week, maintaining constant pressure on German forces despite being surrounded. Captain Hogan, who had witnessed first SEAL failures in North Africa 26 months earlier, was now commanding Artillery Battalion in Ardennes. His after-action report noted, "We fired 11,000 rounds in 6 days, temperatures ranging from 15°C to 30°C, with guns frequently displaced under fire, 0 hydraulic failures. 2 years ago, half our guns would have been non-operational. The improvement represents difference between holding position and being overrun." Post-war analysis quantified the impact. Artillery statisticians calculated that SEAL improvements increased American artillery effectiveness by approximately 40%, not through increased firepower or accuracy, but through increased availability. Guns that previously spent 30% of time non-operational due to maintenance were now operational 98% of time. This availability translated directly into combat power. Economic analysis revealed extraordinary return on investment. Total cost of PVC seal development, testing, and production conversion, approximately $12 million. Cost per seal, $8. Total seals produced during war, approximately 3 million, equipping 50,000 artillery pieces and providing spares. Total program cost, roughly $40 million, including research, testing, and production. Benefits, estimated 40% increase in artillery effectiveness across entire American force for last 2 years of war. Calculating monetary value of that effectiveness is speculative, but conservative estimates suggest improved artillery shortened European campaign by weeks, saving billions in operational costs and thousands of casualties. Artillery's ability to provide sustained fire support enabled infantry advances with reduced casualties. Ability to suppress enemy artillery protected American positions. Ability to destroy fortifications reduced need for costly direct assaults. Dr. Sir Waldo Seaman, whose PVC compound enabled these improvements, received Army-Navy E Award for Excellence in Production in 1944. He continued developing PVC applications after war, eventually holding over 100 patents. But he considered artillery seal his most important contribution. In 1981 interview, aged 84, Seaman reflected, "I developed many materials with commercial value. PVC products generated billions in revenue, but artillery seal saved lives. When I learned that improved reliability meant fewer soldiers killed assaulting fortifications, because artillery could suppress defenses effectively, that mattered more than profits." German artillery engineers interrogated after war expressed frustration similar to their submarine counterparts. Dr. Friedrich Engelmann, chief engineer at Krupp Artillery Division, examined PVC seal samples during technical exchange in 1946. "This is superior material for application. We had similar research programs investigating synthetic seals, but military priorities focused on increasing production of existing designs rather than improving reliability through material science. This was strategic error. Small improvements in component reliability compound into significant operational advantages." The comparison with German approach was instructive. Germany had excellent artillery. The 88mm gun was legendary. The Naval-Werfer rocket system was innovative, but German focus was adding new weapons rather than perfecting existing ones. America took different approach. Make what we have work perfectly. The PVC seal exemplified this philosophy. Don't redesign the gun. Redesign the component that makes gun unreliable. Simple principle. Profound impact. PVC seal technology spread beyond artillery. By 1944, Ordnance Department recognized that hydraulic seals were critical components across military equipment. Tanks, aircraft landing gear, naval gun mounts, construction equipment, all relied on hydraulic systems. All suffered from seal degradation in harsh conditions. PVC compounds developed for artillery were adapted to these applications. Sherman tank hydraulic systems received PVC seals in 1944. Previous seal failures had caused transmission problems, turret traverse failures, and suspension issues. With PVC seals, mechanical availability of Sherman tanks increased from approximately 75% to 90%. That 15% improvement meant approximately 500 additional tanks operational at any time in European theater, equivalent to adding entire armored division without building new tanks. Aircraft benefited similarly. B-17 and B-24 bomber landing gear used hydraulic systems sealed with natural rubber. High-altitude operations, where temperatures dropped to 50 degrees Celsius, caused rubber to become brittle. Landing gear failures were common, resulting in belly landings that destroyed aircraft even when crews survived. Modified PVC seals, formulated for cold temperature flexibility, reduced landing gear failures by 80%. Number of bombers lost to mechanical failures decreased significantly. Naval applications were particularly challenging. Ships' gun mounts, especially 5-inch dual-purpose guns and 40mm anti-aircraft guns, operated in salt spray environment that degraded seals rapidly. Guns often failed during extended engagements when seal degradation caused loss of hydraulic pressure. PVC seals resistant to salt water and ozone dramatically improved reliability. During kamikaze attacks off Okinawa in 1945, American anti-aircraft guns maintained continuous fire for hours, something impossible with previous seal technology. The cumulative effect was transformation of American military logistics. Maintenance burden decreased across all equipment types. Spare parts requirements declined. Mechanical availability increased. These improvements freed resources. Fewer replacement parts to manufacture and ship meant more ammunition and fuel could be transported. Fewer maintenance personnel needed meant more combat troops available. The SEAL, invisible component costing few dollars, generated cascading benefits throughout military supply chain. British military requested access to PVC SEAL technology in late 1944. American government authorized technology transfer under Lend-Lease. British artillery began receiving PVC SEALs in 1945, too late for widespread implementation before war ended. But British engineers immediately recognized value. Post-war, British Army completely converted to PVC SEALs across all hydraulic applications. Soviet Union, through intelligence channels, acquired PVC formulations and independently developed similar compounds. By 1950, PVC-based hydraulic seals were global standard for military applications. The technology that began as emergency solution to North African artillery crisis had become foundation for modern hydraulic engineering worldwide. Korean War in 1950 validated long-term durability of PVC SEAL technology. American artillery deployed to Korea included both World War II vintage guns and newer M101 105mm howitzers. All used PVC seals developed during previous war. Many guns were pulled from storage after sitting unused for 5 years. Maintenance inspections revealed that seals stored properly showed minimal degradation. PVC's chemical stability meant it didn't deteriorate significantly during storage, unlike natural rubber which required replacement after extended storage. Combat conditions in Korea were severe. Extreme cold in winter, temperatures to 40 degrees, extreme heat in summer, temperatures to 110 degrees, mountainous terrain requiring constant gun displacement, and sustained firing during major battles like Pusan Perimeter and Chosin Reservoir. Artillery performed flawlessly. SEAL failure rate remained under 1% throughout war, remarkable considering some guns were firing SEALs manufactured 10 years earlier. But Korean War also revealed limitation. PVC seals, while far superior to earlier materials, still degraded under most extreme conditions. At Chosin Reservoir in winter 1950-51, some artillery operated in temperatures below 50 degrees for extended periods. At these extremes, even PVC became stiff, and hydraulic fluid became so viscous that guns couldn't recoil properly. Engineers developed improved formulations with better low-temperature performance, introducing plasticizers that remained effective at lower temperatures. Vietnam War presented different challenge. Extreme heat and humidity combined with jungle environment, fungal growth, corrosive vegetation, and constant moisture tested seal durability. Again, PVC seals proved superior to alternatives, but Army developed further improvements. Fungicide additives, improved surface treatments, and protective coatings. Each generation of seals incorporated lessons from previous conflicts. Modern artillery continues using descendants of Siemens' 1943 PVC compound. M1777 155mm howitzer, current lightweight artillery system, uses fluoroelastomer seals more advanced than PVC, but based on same principle, synthetic polymer resistant to ozone and chemical attack, formulated specifically for extreme conditions. Cost per seal, approximately $45 in modern dollars, reflecting improved performance but same order of magnitude as World War II seal when adjusted for inflation. The progression demonstrates principle of incremental improvement. Original Buna N seals worked adequately in peacetime. Combat revealed inadequacy. PVC seals solved immediate problem. Subsequent refinements addressed edge cases and extreme conditions. Each improvement built on previous generation. This is how military technology typically advances, not through revolutionary redesigns, but through systematic identification and correction of failure modes. Artillery seal development became case study in military technical training. Officers studying logistics and maintenance learned seal history as example of how small component improvements compound into strategic advantages. The broken seal in North African desert, dramatic failure that revealed systemic problem, had been transformed into institutional knowledge about importance of materials science and military effectiveness. The human dimension of SEAL story often gets overlooked in technical histories. But for artillery crews, SEAL reliability meant something profound. Trust in their equipment. Artillerymen loading 100-pound shells and firing guns generating forces that could tear steel had to trust that recoil system would function correctly. When SEALs failed, that trust eroded. Crews became hesitant, wondering if next shot would cause catastrophic failure. Staff Sergeant Michael Romano served with 32nd Field Artillery Battalion in North Africa and Italy, described the psychological impact in oral history interview decades later. When SEALs were failing in North Africa, we were scared of our own guns. You'd fire a shot and watch the recoil mechanism, wondering if this was the one that would break. After we got new SEALs, don't remember exactly when, sometime before Sicily, that fear went away. We knew the gun would work. That confidence changed everything. We fired faster, more accurately because we trusted the equipment. Trust enabled aggression. Artillery forward observers could call for fire missions knowing guns would deliver. Infantry commanders could plan attacks assuming artillery support would be reliable. Logistics officers could calculate ammunition requirements without factoring in high failure rates. These intangible benefits, confidence, trust, psychological security, don't appear in statistical analyses but profoundly affected combat effectiveness. Contrast with German artillery crews, who faced declining reliability as war progressed. German accounts describe increasing anxiety about equipment condition. Veteran artillery NCO captured in 1945 told interrogators, "In early war, our guns were excellent, best in world, we believed. By 1944, we never knew if gun would fire properly. Seals leaked, hydraulic fluid was low quality, replacement parts didn't fit correctly. We fired less because we feared destroying our own guns. This gave Americans advantage beyond their numbers." The psychological dimension extended to civilian workers manufacturing SEALs. Women working at Goodrich Company factories knew their products were used in combat. Company published newsletter featuring letters from servicemen thanking workers for reliable equipment. One letter from artillery officer in France was reprinted in November 1944 issue. "Don't know who made the seals in our guns, but whoever you are, thank you. We fired 8,000 rounds last month and every gun worked perfectly. That reliability saved lives, probably including mine. Your work matters more than you know." Workers responded with pride and increased productivity. Goodrich SEAL production increased 20% between mid-1944 and war's end, not from additional factory capacity, but from workers volunteering extra shifts and improving efficiency. They understood viscerally that their work had moral significance beyond wages. This connection between manufacturing and combat, mediated through component as mundane as rubber seal, created feedback loop of quality and motivation. After war ended, military conducted comprehensive material science review. Army Research Laboratory, successor to Aberdeen Proving Ground Research Division, published classified report in 1947, Critical Components in Combat Equipment, Lessons from World War II. The report systematically analyzed equipment failures and their causes. Artillery SEALs featured prominently, one of few examples where material science breakthrough had produced measurable operational impact. Report identified pattern. Military specifications often prioritized peacetime performance over combat durability. Equipment tested in controlled conditions frequently failed in chaos of actual war. SEALs were merely most dramatic example. Report recommended systematic review of every military specification asking, does this specification account for worst-case combat conditions? Have we tested beyond normal parameters? Do we understand failure modes under stress? This philosophy became standard in post-war military procurement. Modern military specifications explicitly include extreme testing, temperature cycling from 65 degrees Celsius to plus 165 degrees Celsius, humidity testing at 95% humidity, vibration testing far exceeding normal operations, accelerated aging simulations. Component must prove it can survive beyond expected conditions before being approved. This approach traces directly to SEAL failures in North Africa that demonstrated cost of inadequate testing. Commercial applications of PVC SEAL technology exploded after war. Patent restrictions were lifted as wartime security classifications expired. Chemical industry recognized that PVC compounds developed for artillery had applications far beyond military. Automotive hydraulic systems, industrial machinery, aerospace, oil drilling. Every industry using hydraulic systems adopted PVC seals. By 1960, PVC seals were industry standard worldwide. Waldo Siemens' invention generated billions in commercial value. BF. Goodrich Company profited enormously, but Seaman himself, working on salary as company researcher, received no direct royalties. This was standard practice. Corporate researchers assigned patent rights to employers. Seaman did receive recognition. American Chemical Society awarded him Perkin Medal in 1952, chemistry's highest honor. Citation mentioned artillery seals specifically, for development of polyvinyl chloride compounds enabling reliable hydraulic systems in extreme environments, contributing decisively to Allied victory in World War II, and establishing foundation for modern elastomer technology. Recognition came with irony. Seaman's most lucrative invention, PVC plastic for construction and consumer products, generated far more revenue than seals ever did, but seals had saved lives. In 1970 interview, Seaman was asked which accomplishment he valued most. His answer was immediate: artillery seals. Everything else I did made money or made life more convenient. Artillery seals made difference between men living and dying. That's incomparable significance. He was right. Commercial success is measured in dollars. Military contribution is measured in lives. The broken seal that revealed inadequacy of peacetime specifications led to material science breakthrough that prevented thousands of artillery failures, enabled sustained fire support that protected infantry, and shortened war that was killing millions. The final chapter of SEAL story is about institutional memory. By 1970s, veterans who remembered North African SEAL crisis had retired. Younger engineers, unfamiliar with history, occasionally suggested cost-cutting measures. Do we really need these expensive SEALs? Could we use cheaper alternatives for peacetime training? Proposals periodically surfaced to substitute less expensive compounds for PVC seals in training equipment, reserving expensive seals for combat deployments. Colonel, retired Thomas Hogan, the captain who witnessed first failures in 1942, wrote series of articles for Army technical journals specifically addressing this issue. His 1978 article, Why Artillery Seals Matter, Lessons from Tunisia, became required reading in artillery officer training. Hogan wrote, "Each generation must relearn that reliability isn't luxury, it's necessity. The $5 we save per seal by using inferior materials costs thousands when gun fails in combat. We learned this lesson expensively in 1942. Let's not learn it again." Hogan's warning was prescient. In 1980s, during defense budget constraints, some artillery units did substitute cheaper seals for training. Predictably, failure rates increased. Guns that should have lasted 10,000 rounds before overhaul were failing after 3,000. Training realism decreased because crews couldn't rely on equipment. When these units deployed to Gulf War in 1991, they required emergency seal replacement before combat operations. The experiment with cost-cutting was quietly abandoned. Modern military now maintains institutional memory through systematic documentation. Every component with combat history is flagged in supply system with historical notes. When procurement officer reviews SEAL specifications, system displays notification, "This component critical to artillery reliability." See historical case study, North African Campaign 1942-43. The notification links to detailed history of SEAL failures and solutions. It's small measure, but it works. Proposals to substitute inferior seals are now automatically reviewed by Materials Engineering Board familiar with history. Artillery seals remain in production 75 years after Seaman's breakthrough. Modern formulations are more sophisticated, fluoroelastomers and perfluoroelastomers with even better performance, but principle remains identical: synthetic polymer resistant to ozone and chemicals, formulated for extreme conditions, tested beyond normal parameters. Cost remains similar, approximately $45 per seal in current dollars, compared to $8 in 1943 dollars, roughly $140 in current dollars when inflation adjusted. Modern seals are actually cheaper in real terms while being more capable. The progression from broken seal in North African desert to modern fluoroelastomer seal in M777 howitzer represents 75 years of continuous improvement. Each generation built on previous. Each conflict revealed new requirements. Each failure triggered refinement. It's unglamorous history. No dramatic battles. No heroic individuals. Just patient engineering iteration. But this unglamorous work created artillery that works reliably anywhere, anytime. That reliability saves lives. Always has. Always will. The true climax of this story isn't in any single battle or technological breakthrough. It's in the accumulated moment when artilleryman pulls lanyard to fire gun and knows, absolutely knows, that recoil system will function correctly. That moment of certainty, repeated millions of times across decades of conflicts, represents ultimate success of engineering. Technology so reliable it becomes invisible. Consider what that moment requires. Somewhere, materials scientist understood polymer chemistry well enough to formulate compound that wouldn't fail. Somewhere, manufacturing worker mixed ingredients precisely according to specification. Somewhere, quality inspector tested sample and certified it met requirements. Somewhere, supply sergeant stored seal properly so it didn't degrade. Somewhere, maintenance crew installed seal correctly. All these actions, performed by people separated by time and distance, converged in single instant when artilleryman fired gun and seal held. This is profound trust, not faith. Faith believes without evidence. Trust is confidence backed by accumulated evidence of reliability. Every time seal held, it built trust. Every gun that fired 10,000 rounds without failure strengthened confidence. Over decades, across millions of rounds fired, pattern established. Seals don't fail. Artillery crews stopped worrying about hydraulic systems the same way they stopped worrying about whether steel barrel would contain explosion. It was reliable enough to take for granted. That transition, from concern to confidence to assumption, marks successful engineering. Components that require constant attention have failed their purpose. Components that work invisibly have succeeded. Artillery seal achieved that success because engineer looked at broken seal and saw opportunity rather than just failure. Because corporation invested in research without guaranteed return. Because military was willing to change specifications mid-war. Because thousands of workers manufactured seals carefully. Because maintenance crews installed them correctly. All these contributors, most anonymous, created reliability that saved lives they never knew and never met. Artillery crew in Korea in 1951, firing gun with seal manufactured in Ohio in 1944 by woman whose name nobody recorded, depending on chemical formulation developed by scientists who never saw combat. That chain of dependence, mediated through rubber compound, exemplifies how modern military functions. The broken seal revealed we were trusting wrong material. The fixed seal, PVC compound resistant to ozone and temperature extremes, proved we could do better. And that lesson extends beyond artillery. Whenever system fails, ask whether we're using right materials, right processes, right specifications. Don't assume initial design was optimal. Be willing to change fundamental components if evidence demands it. The $5 seal that replaced $3 seal wasn't cost increase. It was investment in reliability that paid dividends in every round fired thereafter. In 2015, U.S. Army celebrated 70th anniversary of VE Day with ceremony at Aberdeen Proving Ground. Among items displayed was M1 150 mm howitzer, serial number 1847, that had fired 12,473 rounds during World War II across North Africa, Sicily, Italy, France, and Germany. The gun, restored to firing condition, was demonstrated for assembled veterans and dignitaries. It fired perfectly, recoil mechanism functioning smoothly, barrel returning to battery precisely. Maintenance records showed the gun still had original PVC seals installed in 1943, 72 years old, still functional. Preservation engineer examining the seals afterward noted they showed compression set, permanent deformation from decades under pressure, but maintained seal integrity. Material hadn't become brittle or cracked. Chemical structure remained stable. The seals could probably function for another decade before requiring replacement. This longevity was testament to Siemens' formulation. He hadn't just solved immediate wartime problem. He'd created material with intrinsic durability beyond anyone's expectations. The story of how broken seal helped American artillery outlast German Blitz is ultimately about adaptability. American military in 1942 faced humiliating reality. Equipment designed to high standards failed in combat. Response wasn't to blame soldiers or commanders. Response was to identify root cause, inadequate materials, and fix it systematically. This required admitting failure, allocating resources to unglamorous problem, accepting solutions that required changing established specifications, and implementing changes rapidly across global military force. Germany, facing similar technical problems, couldn't achieve similar adaptation. Their industrial base, under bombing, couldn't support rapid innovation. Their military bureaucracy, rigid and hierarchical, struggled to implement changes quickly. Their material science, though excellent, focused on developing new weapons rather than perfecting existing ones. Result was declining reliability as war progressed, exactly opposite of American trajectory. Small component, rubber seal costing few dollars, became leverage point where American industrial and scientific capacity transformed into military advantage. That transformation wasn't inevitable. It required recognition that small things matter, willingness to prioritize reliability over cost, and industrial capacity to manufacture solutions at scale. Today's military still depends on descendants of Siemens Seal. Every artillery piece, every tank, every aircraft with hydraulic systems uses seals descended from PVC compounds developed in 1943. They're more advanced, chemistry has progressed, but lineage is direct. Broken seal in North African desert triggered chain of innovation continuing 80 years later. Sometimes most important technologies are the ones nobody notices until they fail. And sometimes the highest achievement is creating something so reliable that people forget it exists. Artillery seals achieved that. They enable violence, yes, but they also protect those who must exercise violence when no alternative exists. That's uncomfortable truth, but truth, nonetheless. The seal holds. Always has. Hopefully always will.